Hello students, in our previous lectures we have studied about what happens when the AC is applied to a resistor, and this is the circuit for that. Also we have studied about the phasor diagram related to the resistor connected to AC. Then we have studied about what happens when AC is applied to an inductor, and this is the figure. Then related phasor diagram as well as waveform of V and I versus omega t. Then we studied about what happens when the AC is connected to a capacitor. So students, individually when the resistor is connected, then when the inductor is connected, and then when the capacitor is connected, we have studied about the behavior of the circuit, their phase diagram, and the phase angle between current and the voltage in that circuit. Now, in our today's lecture, we are going to start with a topic in which all the three components, that is resistor, inductor and capacitor, they are connected with a AC voltage or AC source. You can see that here resistor, capacitor and an inductor, they are connected in series. So now we are going to study about such type of circuit. So topic number 7.6, AC voltage applied to a series LCR circuit. So now students, you can see here the source voltage is given by V is equal to Vm sin omega t as usual. Let us give this equation number 1. Now applying Kirchoff rule to this circuit, we get V is equal to, this V is nothing but is source voltage, is equal to voltage across resistor plus voltage across capacitor plus voltage across inductor, because we know that whatever the voltage is supplied by the source, that voltage gets distributed across its components which are connected in series, and so the total voltage of these three components R, C and L is equal to the voltage of the source, and that's why I have written this equation first. Now we know that according to Ohm's law, voltage across resistor is IR. This we have applied for AC circuit with only resistor. Then VC is equal to Q by C. This way we have applied for the circuit, AC circuit consisting only capacitor, and voltage across inductor VL is equal to L di by dt. This also we have used for AC circuit consisting only inductor. Now using these values in above equations, we will get V is equal to IR plus Q by C plus L di by dt. Let us give this equation number 3 and this as number 2. Now students, there are two methods to determine the instantaneous current small I and its phase relationship to the applied voltage. Means for this given circuit of LCR in series, we can find the instantaneous current I and the phase difference between I and V, that is phi, by using two methods. First is by Phasor method and the other is by analytical method. In analytical method, more mathematics is used. In Phasor method, the Phasor diagram helps us to get this I and phase difference phi. So now let us see first Phasor method. So this is topic number 7.6.1, Phasor diagram solution. Now students, when LCR are connected in series, current in each element, that is L, C and R, these are the elements or the components of the circuit. So current in each component will remain same because they are connected in series. So that current can be given by I is equal to Im sine omega t plus phi. Now students, there must be some phase difference phi between current and the voltage, because we know that voltage is given by this equation, and we know that when these components are connected across the circuit, there will be some phase difference between V and this current I. So this is the phase angle or phase difference between V and I. So now, considering this as the equation of the current, where phi is a phase difference between V and I. Now let I, capital I, represents the phasor of current. Then capital VL, capital VR and capital VC will be the phasors which represents the voltage across these components L, C and R. Students, the voltage drop across each component will be different, but the current is same in each component because these are connected in series. That's why this is common for all the components. Phasor I is common for all the components, but potential difference, that will be different. Now you can see here, and we have studied in our first lecture that if this is the current phasor, then voltage phasor will be also on the same line. There will not be any phase difference between V and I when only resistor is connected, that we have studied. So they are in same line. Then in our next lecture we have studied that when the inductor is connected, there is a phase of 90 degree, that is phase difference was pi by 2 between I and V across inductor. And in that case, we know that current lags behind the voltage. Then in our third lecture, we have studied for the circuit consisting only capacitor. In that we have studied that current phasor and voltage phasor, once again they make an angle 90, that is pi by 2. But in this case, current leads the voltage by pi by 2. So it is clear that this VL, this phasor VL and VC, they are mutually opposite, and if we consider VC greater than VL, then resultant of these two will be VC plus VL. This is phasor form of this voltage, resultant voltage of VL and VC. So as here we have considered VC as greater than VL, so VC minus VL is nothing but it is this vector. Student, here plus is shown, it is because this is a vector addition. Which vector? A rotating vector addition, that's why it is plus taken here. Otherwise actually what happens, it is voltage across capacitor minus voltage across inductor. Now result of this two is obtained, which is this. Still there is one more VR along the line of current, that is VR here. So now a result of all the three phasors can be given by this voltage V. This V is result of which? Result of this as well as this. So students, I hope you understand this phasor diagram. Here you can see that this line represents VCM minus VLM, means this is a voltage across capacitor and voltage across inductor, and this gives the maximum value. M shows the maximum value of these voltages. So now once again come to this. Here the length of the phasors, that is amplitude, means maximum values, is given by VRM, that is maximum value of voltage across resistor, is equal to IMR. Similarly VCM is equal to IM into XC and VLM is equal to IM into XL. This we have studied in our previous lectures. Now phasor relationship, that the resultant voltage V, what is this V? This is the voltage of the source and its maximum value. This is voltage supplied from the source and its maximum value in the form of phasor is given. So that V is equal to VR plus VC plus VL. This is not a new equation, students. This is same as this, but now the maximum values, or this equation is written in the form of phasor, that's why it is capital V. Now next is, as I explained from the figure, result of the VC and VL is given by VC plus VL. Now writing this equation, as this VCM and VLM, they are on the same line and VCM is greater than VLC and they make a right angle triangle. You can see once again to this figure. Here this makes a right angle here, as well as if you consider this two like this, then also this is a right angle triangle, in which this is the hypotenuse and this is VRM and this side is the difference of VCM minus VL. So we can apply the Pythagoras theorem and we can write that this Vm square, that is this hypotenuse square, is equal to sum of the squares of this as well as this. So we have considered the maximum values and we have written this now. Vm square is equal to Vrm square plus Vc minus Vlm square. So Pythagoras theorem is applied. Now substituting values of equation 5 in 7. This is equation number 7 and values of equation 5 are this. So now in place of Vrm we are going to write Imr. In place of Vcm we are going to write Imxc. In place of Vlm we are going to write Imxl. And so we will get this. Values are kept from equation 5. Now you can see Im is common in all the terms and it is square of that. So Im square is taken out. So now taking Im square, what is remained here? R square. And when the Im square is taken out, what is remained here? Xc minus Xl square. So this is a simple mathematics. Simply we have taken out Im square common. Now just make the subject Im square. If we make the subject Im square, this term will be towards the left side and it will be in the denominator. So we will get Vm square upon this term. But still it is Im square. But I want simply Im. So after that we have to take the square root on both the side. So taking square root on both the side, we will get on left side simply Im, that is this square root of this term, and on other side we will get square root of Vm square, that is Vm, and then square root of this term which was brought on this side. So here it is square root of this term. Again students, this is a simple mathematics, you can easily do it, but I'll advise you to sit with a pen and a paper so that you can do this mathematical steps simultaneously with this video. Now let us give this equation number 8. Thereafter we know that this type of equation resembles the Ohm's law. We know that I is equal to V by R. You can see here there is term with I, here there is term with V. So whatever the term remain here, that is similar to the resistor. Whatever the work is of resistor in a resistive circuit, the same work is done by this term in a LCR series circuit, and this term is called the impedance of the circuit, denoted by Z. Students, we know that if only inductor or only capacitor was there, then we call that term as a capacitive reactance or inductive reactance. But here all these three are connected, and so resultant of all these terms, they give us this value which is known as impedance of the circuit, denoted by Z. So definitely we can say now Z is equal to root of R square plus XC minus XL square. Unit of impedance is same as that of resistor. Now we have denoted this by Z. So now Im is equal to Vm upon Z, that I have written here. So students, once again, the function of impedance Z in LCR AC circuit is analogous, that is similar to the resistor R in resistive circuit. Now students, since phasor I is always parallel to phasor VR, the phase angle phi is the angle between VR and V. Here this VR is the phasor of voltage across resistor and this V is the phasor of a source, and their angle will be always phi. Students, this is not new figure. This is the figure obtained from this phasor diagram. This is the same figure. Writing this VRM in terms of resistor R, this side which is VM in terms of Z, because total impedance is Z, and this side which is having terms VCM minus VL can be written as XC minus XL. So there is R, there is Z as hypotenuse, and XC minus XL is also other side. So same figure is here. You can see hypotenuse is Z and the other two sides are R and XC minus XL. And so this is the phase angle between the current and the voltage V, or we can say that VR and V. Now from this figure, tan phi with respect to this angle phi, tan phi is nothing but it is opposite upon adjacent, and opposite is XC minus XL and adjacent is R. So you can see first here tan phi is XC minus XL upon R, but the same can be written in terms of voltages. This is from previous figure, that is this figure. You can see here also with respect to angle, tan phi is opposite, which is this, and adjacent is this. So we get these two equations for tan phi. One is this and the other is this. Now equation 9 and 10 are graphically shown in figure 3 called impedance diagram. Which two equations? 9 and 10, that is this equation, and equation number 9 is an equation of impedance. So this can be graphically represented as this impedance diagram. This figure is known as impedance diagram. Now finally students, if XC is greater than XL, then phi, angle phi will be positive, and in that type of circuit the circuit will be mostly capacitive. Predominantly capacitive means mostly it behaves as a capacitive circuit, and we know that in a capacitive circuit current I leads voltage by phase phi. So this is for this condition that Xc is greater than XL. So Xc is having its more effect. So capacitive circuit. But what happens if Xc is less than XL? Then this angle phi will be negative, because in this formula you can see that if this value is greater than this value, then this term in the numerator will be negative, and so tan phi is also negative, and as a result phi will be negative. And so in such case, as XL is greater than XC, the circuit will be mainly inductive. It will behave as an inductive circuit, and we know that in inductive circuit current I lags the voltage by phase phi. Here it is V. So in this case current leads, but in this case current lags behind the voltage by phase phi. Now here this figure is nothing but it is the combination of phasor diagram and the graph of omega t and I and V. So here you can see the angle between I and V is denoted by phi, and according to voltage equation of source, it always starts from 0 and it moves in this way with respect to omega t. But for LCR circuit, we know that current will not start from the same point, because there is some phase angle between V and I. So here the current starts from this point. And clear that the maximum value of V and maximum value of I, they have some difference between them, and that difference is nothing but it is phase phi. So this figure shows this condition when Xc is greater than XL. So students, I hope you understood about the first method of obtaining I and phi, that is phasor diagram solution. Now next will be analytical solution for this LCR circuit connected to AC. Now here in this topic 7.6.2 we will study about analytical solution. Once again, as usual, V is equal to Vm sin omega t, that is voltage supplied from the source. Let us give this equation number 1. Now next is voltage equation for the circuit. Voltage across inductor is given by L di by dt. Voltage across resistor is R into I, and voltage across capacitor is Q by C. And addition of all these three voltages will give the voltage of the source, because these components are connected in series. Let us give this equation number 2. Students, these are not new terms for you. This we obtained when the only resistor is connected. This we used when only inductor was connected, and this we used when only capacitor was connected. Now here all the three are connected in series, so all the three terms are there. Now students, we know that current I is dq by dt, and so if we differentiate this equation with respect to time once again, Then on left side we'll get di by dt. On right side it will be d square q upon dt square. You can see already there was q in differentiation form, but when we differentiated once again with respect to time, this is the second order differentiation is obtained of charge. So now putting this value of I, that is dq by dt here, and di by dt is equal to d square q upon dt square here, we get L d square q upon dt square plus R dq by dt plus q by c, this term is as it is equal to Vm sin omega t, because we know that V is equal to Vm sin omega t from equation number 1. Student, this equation is the second order differential equation of charge. Why it is second order? Because there is d square q upon dt square term is there. So it is a second order differential equation of charge, and this equation is similar to the equation of forced damped oscillator. In standard 11 we studied about the oscillation. In that there is an equation of damped oscillation as well as forced oscillation. So this equation resembles that equation of forced oscillation. And so the solution of this equation can be given by q is equal to qm sin omega t plus phi. This is the solution of this equation. Students, we know that any equation has its solution. If there is a linear equation, then also it has a solution that you have studied in 10th standard. If there is a quadratic equation, then also it has a solution. And we know that for a quadratic equation, we get two solutions. Similarly here, this equation for LCR circuit is this, and its solution is given by this in terms of charge. So we accept this equation as a solution. Now differentiating this equation with respect to time, on left side we get dq by dt. Differentiation of q is dq by dt, and on right side we know that this qm is constant, so differentiation of sine omega t plus theta will be sine will become cos. So differentiation of sine is cos, and as this omega is related to function time, but omega is constant, and in differentiation we used to multiply that constant. The constant which is with this t, that is to be multiplied. So sine theta will become cos, consider that this as a theta, so sine theta will become cos theta, but here this omega according to chain rule will be here. Once again differentiating this equation with respect to time, we get on left side d square q upon dt square. This is first order, and then we differentiate second time, then it will be second order. So we have differentiated on left side, we got this equation, and on right hand side this qm into omega is constant, and differentiation of cos is minus sine. You can see minus is kept here, so minus sine theta. This is theta, suppose. So cos theta will become minus sine theta, but once again this omega is to be multiplied. So here you can see there is an omega square, because according to chain rule this omega is multiplied. Now we got these three equations, equation number 4, 5 and 6. So using these equations in above equation, in place of q we are going to write this, in place of dq by dt we are writing this, and in place of d square q upon dt square we will write this. So students, here in this equation we are going to place value of this, value of this and value of this. So next will be this L into value of d square q upon dt square, then R value of dq by dt, and then 1 upon c, and value of q is this Vm sin omega t as it is. Now in all these terms on left hand side, here q and omega is there, here also q and omega is there, here only qm is there, there is no omega. So what we'll do, we'll multiply omega and divide by omega. So now we can say that in all these three terms there is q into omega which can be taken out common. In short, when we take out q omega common, what is remain in this first term? L is remained, 1 omega is taken out, so 1 still remained, minus sign as it is, sin omega t as it is. Then in second term, when this q and omega is taken out, what is remained? R cos omega t plus theta, and so it is this. And finally in this term, when omega q and omega is taken out, what is remained? Because here there was no omega, we have multiplied and divided by omega. So when this q and omega was taken out, what is remained? 1 upon omega c is remained, which is here, and then sin omega t plus theta. Right hand side is as it is. So simple mathematical steps are there. Then we know that this r cos omega t plus theta we are writing first. Now for remaining two terms, omega L can be written as XL, and 1 upon omega c is nothing but it is XC. Then sin omega t plus theta here also, and sin omega t plus theta here also. So it is common in both the remaining terms. For these two terms, sin omega t plus theta is common, so it is taken out. What is remained? XC minus XL. Once again, for these two terms, sin omega t plus theta is common, that is taken out. What is remained? XC and minus XL. And on the right hand side, it is same. I have mentioned here that omega L is XL and 1 upon omega C is XC. Now multiplying and dividing above equation by impedance Z. This equation is multiplied and divided by impedance Z. So you can see here on left hand side Z is multiplied here, as well as we have to divide it. So what we did, multiplied Z here and dividing that Z in all the terms. So it is multiplied and divided. Or in other way I can say that if I multiply and divide by Z, this z is kept as it is here, and this z is taken inside the bracket. So that z will be here also below r as well as below xc minus xl. So you can see here z multiplied is here and divided is here in both the terms. But what is z? Z is impedance, which is given as root of r square plus xc minus xl square, that we know only. Now students, once again this is the impedance diagram which we have already studied in phasor diagram method, and from this figure it is clear that r by z is equal to cos phi, xc minus xl upon z is sin phi, and xc minus xl upon z is tan phi. From this figure you will get it. So now here in place of this r by z we are going to write cos phi. In place of xc minus xl upon z we are going to write sin phi. So we'll get next equation as this term is as it is, cos phi rest of the things, sin phi rest of the thing as it is. On right hand side also this is same. Then applying trigonometric rules or formulas, if it is cos phi cos omega t plus theta plus sin phi and sin omega t plus theta, then we can apply this equation cos a cos b plus sin a sin b. You can see this is your a and this is your b, so it is cos a cos b plus sin a sin b. So if it is like that, then we can simply write this as cos a minus b. So I have written here cos a minus b, or cos b minus a, meaning is same because cos is an even function. So if we write this phi minus this or this minus this, meaning will be same, as cos is an even function. So I have written this cos omega t plus theta minus phi, and on right hand side Vm in place of sin omega t we are going to write cos omega t minus pi by 2, because we know that sin a is equal to cos a minus pi by 2, or we know that sin theta is equal to cos theta minus pi by 2, or pi by 2 minus theta, meaning is same. So here you have to take care for this. You should remember this formula for trigonometric functions. Now next step, comparing both the sides of this above equation 8, this equation. If we compare both the side, then you can see that here it is cos, here also it is cos. So Vm should be equal to this. So I have written Vm is equal to Qm omega z, and this should be equal to this. So we can write that, see, omega t is on both the side, so that is not considered. So theta minus phi is equal to minus pi by 2. So after comparison we will get theta minus phi is equal to minus pi by 2. Then after this equation, this is z impedance, it is similar to the resistor. So this term should be the maximum value of current, because this is the maximum value of voltage, and according to Ohm's law we know that V is equal to IR. So similar to that we get IMZ, and here making theta subject, this phi is brought towards next side, so it will become positive. So phi minus pi by 2. I have mentioned that here this Im is nothing but is qm into omega. Now the current in the circuit is I is equal to dq by dt. This we have used and we also obtained this. So this we have already done. Now next step, qm omega is nothing but is Im, and in place of this theta, here we can write phi minus pi by 2. So that we have done. In place of theta we have written this from this equation number 10 I have mentioned here. Then once again, cos a minus pi by 2 is equal to sin a. So here also cos, this is your a minus pi by 2 is equal to sin a. So this is sin and a is nothing but is omega t plus phi. So applying this relation, we get this equal to this in terms of sine. Now here this Im is nothing but it is Vm upon Z. But what is Z? It is root of r square plus in bracket xc minus xl whole square. Vm as it is. Angle phi is tan inverse of this. So these are now nothing new for you. This is obtained from figure only. From figure you can say this. So finally I have written this. Current I is equal to voltage upon resistor, but here not only resistor is there, all the three component is there. So there is impedance for all the three components, that is denoted by Z. So students, I hope you understood about analytical method. Do paperwork for this.